Solving for x analytically, not by graphing, what you want to do is whenever you're solving and you have an exponential equation, this is an exponential equation because we have x in the exponent, we want to isolate the base of the exponent. So the base of the exponent's 8 and there's nothing else around it. So for example, there's not like 3 plus 8 or this expression minus something else. So now that I have it isolated, I'm going to take the log of each side. So I do log 8 of 2x plus 1 equals log 100. So I can use the property of logs, and since 2x plus 1 is an exponent, that's actually going to be the coefficient, or out front, the expression out front. So it's going to be 2x plus 1 times log 8 equals log 100. Now log 8 and log 100 are just numbers that I can divide by, so I can divide both sides by log 8. And so to solve for x on the left hand side, I'm going to take log 100 divided by log 8, and then I'm going to subtract 1 because that's going to get rid of this positive 1, and then divide everything by 2. So I'm going to put that in my calculator. So when you put it in your calculator, make sure that after log 100 that you close the parentheses. So it's log 100, close the parentheses, log 100, so I did log 100 divided by log 8 minus 1 and divided that all by 2, and I got approximately 0.61. So go ahead and put that number back in for x and see if you get 100. So make sure you store it in your calculator when you're checking it. Number 2, to solve by graphing, what you want to do is you want to put one side into y1 of the equation and the other side into y2. So this is going to be an exponential growth equation. So this will be a growth right here. It'll be very steep. And this 1,000 is going to be a horizontal line at y equals 1,000. So in order to see that intersection, you have to make sure that your y-axis is going past 1,000. So make sure you change your window to be at least 1,000 for the y-max. So I'm going to change my y-max to 1,200. And so it's going to go from 0 to 1,200 right here. And so you should have two functions, 12 plus 6 to the 3x power, and then I'm also going to have the function just y equals 1,000. So when you do this, what you want to do is press the second trace button. So second trace will give you options for intersect. So intersect, you're going to want to put your highlighter right over here and on your graphing calculator and press enter 3 times. And that will give you the intersection. So 1, 2, 3. So the intersection is about 1.28. And again, this is definitely, you want to check plug your answer back in for x and see if you get 1,000. If you rounded this and you plug it back in, it's not going to be exactly 1,000. Alright, solve and round to nearest tenth. So this is a logarithmic equation. What you want to do is write it as a single log, and it's already written as a single logarithm. So I'm going to write it as log base 10 of 2x. Remember, if there's not a base given, you can assume it's base 10. That's our common logarithm. So now I'm going to write this as an exponential equation. 10 to the 4th equals 2x. So then to solve for x, I just do 10 to the 4th divided by 2, and I get 5,000. Okay, number 4, write it as a single logarithm. So this is a natural log, but I can write it as a single natural log. So first, I'm going to notice that each of these coefficients or expressions out front are going to turn into the exponents. So minus natural log, natural log of y cubed plus natural log of, this is actually the cube root of z. Okay, z to the 1/3 is the same thing as the cube root. So now I can combine these, remembering that the property of subtraction makes this expression into go in the denominator. Addition makes this go in the numerator. So I'm going to start out with natural log. X to the fourth is going to go in the numerator because it's a positive. Y to the third is going to go in the denominator because it's negative. And the cube root of z is going to go in the numerator. Okay, so I have written it as a single log. So it can be a natural log or a logarithm for that type of problem. Okay, number 5, to solve, I want to isolate the natural log, so I'm going to divide both sides by 2. So I have natural log of 3x plus 1 equals 2. So the natural log, by definition, is the same thing as log base e. So I'm going to write it as log base e of 3x plus 1 equals 2. So if I have written it as a single logarithm, I'm going to rewrite this as an exponential equation. So it's going to be e squared equals 3x plus 1. Well, e squared is just a number, so I can just do e squared minus 1 and then divide by 3. So doing e squared minus 1 and then dividing by 3 will give me about 2.13. So it's about 2.13. So just make sure if you're putting this all in your calculator at one time that you either put the numerator in parentheses or you can do it in 2 steps. And then an investment compounds continuously. So when you read compounds continuously, you are using the form A equals PE to the RT. So if we know, well, we want to know how long it will take to double. So we're trying to find what T is. So we're given that it's doubling. So I'm going to let A be 2 and P be 1. Because no matter what, if I put this 100, this will be 200. If this is 200, this will be 400. No matter what, I'm still going to end up with 0.052t. I'm still going to end up with 2 equals e to the 0.05t, 52t. So to solve this, I need to take the natural log of each side, because natural log and e are inverses. So natural log 2 equals natural log of e to 0.025, oops, I wrote that wrong, 0.052 t. So using the properties of logs with exponents, this is actually natural log of 2 equals 0.052t times the natural log of e. So natural log of e, since those are inverses, this is just going to be 1. This expression right here is 1, so that cancels out. So now I'm going to divide both sides by 0.052. So I do natural log of 2, close the parentheses, divided by 0.052, and I get 13.33. So about 13.33. So 13.33 years. That's how long it's going to take your investment to double.